Hi students, this is your recording for week 2 for the science support program. You'll be asked to watch an extra video once a week for the next 6 weeks. And after that time you will be asked to take the science checkpoint again that we took a few weeks ago. Today we will be covering Newton's third law, and we will apply Newton's third law to design a system, to design a solution to a problem involving the motion of two colliding objects in a system. Have you ever been hunting? I'm not a big hunter, but have you ever had the chance to shoot a big gun like this guy down here? Well, the question I ask is, sometimes when people hunt, they get these eye injuries right above their eye. They're looking out this scope, and anyway, just to pause here, and what could cause that? All right, perhaps you remembered from class that we've been talking about Newton's third law, that anything that has an action has an equal and opposite reaction. So while the gun shoots the bullet forward, it also kicks the gun back. And if you're not careful, that gun can kick back and you can get some pretty serious eye injuries. So this slide shows basically the summary of Newton's third law, and you guys can read it with me. For every action, there is an equal and opposite reaction. So you see on here that, this guy is pulling this rope, 500 newtons, okay? That's how much, force he is pulling on the wall. But honestly, the wall is also pulling back on him 500 newtons as well. And so it's an equal and opposite reaction. And same here, he's pulling on the elephant's pulling back on him. Now, in this scenario down here, it might end up being that the elephant is, is going to have it's going to throw it out of balance, and there won't be an equal and opposite reaction. The elephant has more force, and so it may pull the guy forward. But we see these kinds of things also in car accidents. For every action, there is an equal and opposite reaction. If I smash my car into another person's car, their car is also going to smash into me. Anyway, it's equal and opposite. So in class, you may remember this slide. I asked you to do a quiet read on this, and if you want to, you can pause this recording and do a quiet read as well, but I can also summarize it for you. When you kick the soccer ball, of course you are going to kick that ball, but that ball also gives you a force back, and it gives you an equal and opposite force that you give to it, which is why, let's say you kick the ball way hard, you could end up with like a bruise or something like that, or maybe you're not wearing your right soccer cleats or something, and you kick the ball. It's going to push back on you with the exact same amount of force. So when you kick a soccer ball, you apply a force to the ball, and it pushes back on you with the same force. Okay, so but if the forces are equal, why does the soccer ball move but you don't? Any thoughts on that? This one's maybe a little bit trickier, but why doesn't, if you're applying equal and opposite force, why does the soccer ball move but you don't? Okay, well, if you had a chance to look at this slide, it gives you the answer. So the answer here is all about mass, okay? There is far more mass to you than there is to the soccer ball. So you are going to stay put while that soccer ball goes flying. Just kind of like in the previous picture a couple ago, I was showing you that elephant and the man. Even though you are pulling on that elephant and the elephant is giving you an equal and opposite reaction, because the elephant is more massive, the elephant will probably move you. Let's take a look at this checkpoint question that we had on the last checkpoint. I'll give you guys a chance to answer it, and then we'll talk about it. So which of Newton's laws best explains why motorists should buckle up? we'll say A, the first law, B, the second law, C, the third law, or D, the law of gravitation. Okay, so let's maybe just go through and review the laws of Newton for just a minute before we answer. So remember, the first law says that an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by some kind of unbalanced force. So I don't know if that would best explain why we should buckle up. You know, and then the second law says the mass of an object is going to change the amount of force you have to put in to move that object. So if I wanted to move a shopping cart that was empty, it would be much easier than moving a shopping cart that is full. So kind of mass's role, the role of mass in, you know, force, how much force is required. The third law, which I hope you put this answer, is all about for every action there is an equal and opposite reaction. So this best explains why we should buckle up, because if we get into car accidents, we would want that safety belt to keep us safe. For every action there is an equal and opposite reaction. So hopefully that makes better sense. I know this was kind of a challenging question on the checkpoint. All right, so we have the classic balloon example and experiment, and I want to talk about how this really illustrates Newton's law very, very well. Yeah, so let me finish blowing up this balloon and we'll see what happens. I'm not going to tie it off, I'm just going to let it go, and you guys already know what's going to happen, but okay, so here we go. There is going to be an action when I let go of this balloon, right? The air inside here, because of the elasticity of the balloon is going to want to collapse, and there is going to be an action of the air blowing out of the balloon, right? So I could even draw that, right? And you guys tell me what the reaction is. I don't know if you could see that. But the equal and opposite reaction, of course, is that while the air is pushing down, that balloon goes up, right? There is an equal and opposite reaction. Now, I could blow up the balloon bigger, and there would be even a bigger equal and opposite reaction, right? So depending on how much I blow up the balloon, I can make the balloon go farther, last longer. So this is a good way to show Newton's third law. Another example here shows just the pushing back on a skateboard. Not much to put here other than just, you know, if there is an action here using the muscles, the reaction is that that skateboard is going to go back. Here is another question I want you to answer from the latest checkpoint. It's a Newton's third law thing. So, okay, so your bat hits the ball. Perfect timing for the World Series if you're watching. Your bat hits the ball to you with a 1500 Newton instantaneous force. The ball hits the bat with an instantaneous force whose magnitude is what? Okay, so is it somewhat less than 1500 newtons, somewhat greater than 1500 newtons, equal to 1500 newtons, or essentially zero? So we'll say A, B, C, or D. What do you guys think? All right, well, I've told you again and again that Newton's third law says that when there is an action, there is an equal and opposite reaction. So it is equal. So I hope that it makes good sense that it is equal, 1500 newtons. We could take a moment to look at this action-reaction game, talk about equal and opposite. We just talked about this one here, the nice baseball bat. But I want you guys to take a moment and write a response to me. How, like, give me just when you write. So my question is write about one of these action-reactions on the page. Tell me what the action is. Tell me what the reaction is. So if you're talking about, you know, the hammer and the nail, the hammer, of course, the action is the hammer hitting the nail, and the reaction is that the nail drives into the wood or whatever. Action of being punched, that's the action. The reaction, of course, is that someone's face is going to get pushed away. They might get a bruise. The action here, not much action on this kitty, but the cat is sitting on the chair and the cat is pushing down on the chair, but that chair is actually also pushing up on the cat. So the cat is able to maintain sitting there. We did this lab in class, and it's going to be a little bit tricky to kind of talk through here, so I won't spend too much time talking about it. But we took these, we kind of did a simulation where we had these balls, and these two, like if the mass of these two balls were exactly the same, so they're both 1.5 kilograms. Okay, and this one is sitting still. Okay, the velocity is 0, it's not moving, but I'm going to send this ball and I'm going to hit it into the other one. Okay, so there's going to be an action and a reaction, and then we also say that we're going to take away all things like friction. We're just going to pretend like these balls are on a frictionless surface, perhaps like an air hockey table or something. You can almost imagine this with like air hockey too. If you had two air hockey pucks, one is sitting still and you're going to push the other one into the other one. What's going to happen? Do you guys have any ideas here? Tell me what's going to happen to the green ball and the red ball. Okay, cool. So I hope some of you may have seen this before, and you could probably even do it. If you have two balls sitting close by, you can set one, you know, by itself, and if you roll the other one into it, this one, when it hits it, it like stops, and that's the action, is the hitting, and the reaction is then that ball continues, that the second ball continues to move forward. So this green ball would continue moving while the red ball would stop. And we did these different simulations in class, and we won't go through them all here, but you can see that, anyway, it's almost too much to look at right here. It's a little crazy, but just remember that the moral of the story is that in Newton's third law, there is an equal and opposite reaction to everything. I do want you to stop, and this is a great video we also watched in class, but I thought it was great and a little bit fun, so take a moment now to stop and watch this video. All right, my friends, thanks for watching. Watch for my recording next week. Email me if you have any questions.